Hello, I'm Apoorva Bisht, and I would be presenting our project which involves intensity correlation measurements for various light sources. Single photons are promising candidates for quantum computing. One of the major goals of our lab is to identify reliable single photon sources to generate single photons on demand. For this, it is important to understand photon statistics for photon sequences generated by light sources. The intensity correlation function gives information about the photon statistics. For example, if the light source is random or bunched or anti-bunched, and also about the source that generated the photon sequence. To this end, we measure the second order correlation function for two light sources, specifically laser, which is random, and thermal light, which is bunched. The expression for second order correlation function is this, where I stands for intensity at time t and tau stands for the time delay. Thus, I of t plus tau stands for the intensity at time after the delay. For stationary light like laser, this function can be calculated to be 1. First, let's talk about the light sources that we use for this project. The first one is laser. Laser is an ideal source of random light. That is, it has uniform intensity for every time delay. Thus, it follows Poisson distribution. So if we have signals from the same laser source at two inputs, they would turn out to be completely uncorrelated to give a G2 of 1 for all times, like so. The second source that we use is a thermal light source, which is a bunched source. Photons in thermal light are not completely random, rather, they are bunched. The bunches shown in this symbol schematic result in higher probability of correlation for smaller time delay. These characteristics are summarized in this table as follows. Now let's move to the experimental setup. The setup consists of a light source, a beam splitter, which splits the incoming beam, and two detectors, PMT1 and PMT2. PMT1 provides the input signal to input 1 of the time to amplitude converter, and PMT2 provides the signal to input 2 of the time to amplitude converter. Input 1 acts as the start signal, whereas input 2 acts as the stop signal. The maximum output of our time to amplitude converter is 10 volts, shown over here. And from the current settings, this 10 volts corresponds to 50 nanoseconds on the time axis. And this 50 nanoseconds corresponds to the time delay tau. So when input 1 first receives a signal, the voltage starts increasing in a linear fashion. The voltage would keep increasing up till 10 volts if it does not receive a photon at input 2. But now let's say that the photon from input 2 is detected at this point. So for example, about 40 nanoseconds. Then the corresponding voltage would be outputted, which is represented as V out over here. This is sent to the multi-channel analyzer implemented using a red pitaya, which is a field programmable gate array, also called an FPGA. The red pitaya has a 14-bit A to D converter, and thus we have 2 to the power 14 time bins or channels, and in each channel we have the data about the corresponding number of photons that we have received in it. The total number of photon pairs that we detect over one reading is of the order of megacounts. There are a couple of major advantages about the system that we use. Two-detector system helps ignore spurious photons and dead photons since they are completely uncorrelated and are equally spread through time for a stationary source. Thus, we are able to take measurements at zero time delay as well. Next, we use a multi-start, multi-stop time to digital converter, which means we use the multiple photons that are received at PMT1 in contrast to just a multi-stop time to digital converter, which would use just one start photon from PMT1. Now, this is suitable for light sources which have high photon flux and have long coherence time, like the laser light that we have used. This results in a much higher efficiency, which is equal to the factor of product of count rate and correlation time of light source compared to the multi-step time to digital converter. Thus, comparing the theoretical predictions with our experimental data, we see that our data is in good agreement with the predictions. Hence, we are ready to use our system for future applications and for more rigorous correlation measurements. As a future plan, we would also implement several improvements to this setup, including improving signal to noise ratio by reducing stray light, reduce the bandwidth of the light incident, and increase coherence time by using pseudothermal light source. We can also reduce dead time effects of both the detector and the counter and find and fix other issues of deviation from the expected G2 function. Thank you.